evaluate the limit as t approaches 0 from the right-hand side of arctan of 1 over t. So it appears to be slightly problematic that we're approaching 0 because t is in the denominator, and obviously anything divided by 0 is undefined. So it seems as though this could be something problematic, and so you might try and do all your different techniques of solving limits that you've come across. You might try L'Hopital's rule, you might try the squeeze theorem, or you might try something along those lines. But the method I'm going to show you doesn't actually involve those, and it's relatively straightforward. So we are going to let 1 over t equal to u. So what we're going to try and do is express this limit now in terms of u. So if we originally had the limit as t approaches 0 from the right-hand side, then we'll notice that as t approaches 0 over here, then our denominator becomes extremely small. And as our denominator becomes extremely small, this fraction will become extremely large. So as it approaches 0, the fraction will approach infinity. So that'll be the same as saying, so the limit as t approaches 0 from the right-hand side will be the same as saying the limit as u approaches infinity. Okay, so now rewriting this limit in terms of u, we have the limit as u approaches infinity of arctan of u. Okay, now this is very straightforward. So first we'll draw our tan graph in case you've forgotten what the arctan graph looks like. And that's pi by 2, it's negative pi by 2, and that's pi by 2. Okay, now the arctan graph is the inverse of the tan. So it's the tan graph reflected about the y equal to x line. So that yields us a graph that looks something like this, where this line now is pi by 2, and this line now is negative pi by 2. So if our input for our arctan graph is approaching infinity, that means we are moving along this graph all the way to infinity. And you'll notice then that the graph actually, or arctan, approaches pi by 2. So therefore, our limit is equal to pi by 2.